Question 26 on the final exam is going to come out of section 3.5. It has not previously been tested. This question is going to test whether you are able to solve an exponential equation. Some of those equations may involve the base e, but could be open to any base in the exponential equation. Alright, in an exponential equation, the first thing that we'd like to do is get the e all by itself. Okay, so I'm going to begin this problem by moving the minus 9 from the left side to the right side. So that would make 4e raised to the 2x equals 12.6. And now we got to move the 4 over, so we're going to divide by 4. That gives us e raised to the 2x equals 3.15. From here, now we need to get rid of the e. And to get rid of the e, we're going to take a natural log of both sides. The natural log in front of the e cancels the e and leaves us with 2x equals the natural log of 3.15. So we're going to divide by the 2, and that gives us x all by itself. So we want natural log of 3.15 divided by 2, and to 4 decimal places, that's going to be 0.5737. The next example is similar to the last one in that I want to get the base completely by itself first. And in this particular problem, the base is by itself, and that there's nothing else added or subtracted behind the base. There's nothing multiplied in front. It is all isolated by itself on the left-hand side. So to begin, we're going to take a logarithm of both sides. And I prefer to still use the natural log. So I'm going to use natural log. If you prefer base 10 log, you could certainly do a base 10 log. Now the difference between this and the last problem is that the natural log doesn't cancel out the 3. The natural log just allows us to take the exponent 4 minus x and move it to the front of the logarithm, as we have a log property that allows that. So we have the quantity 4 minus x times the natural log of 3 equals the natural log of 13. Now we can divide off the natural log of 3. So that gives us 4 minus x equals the natural log of 13 divided by the natural log of 3. I'm going to take the 4 across by subtracting it. Okay, so now we've got negative x equal to, I'll go ahead and compute that on the calculator. To 4 decimal places, that is negative 1.6653. That's negative x, so therefore positive x equals positive 1.6653. The last example is one in which we don't need to use logarithms to solve because we can make the base be the same on both sides. So in this particular problem, I'm going to re-express or rewrite the base. I'll say the bases. The bases on both sides of the equal sign. So the 4 is 2 squared. And just like the 4 was raised to the x plus 2, so is the 2 squared. The 8 is 2 cubed, and that needs to be raised to the 2x. That gives us then 2 raised to the 2x plus 4 equal to 2 raised to the 6x. Once we've made the bases identical, we can cross the bases out or ignore them and just set the powers 2x plus 4 equal to 6x. I'm going to bring the 2x over here, so I get 4 equals 4x. So therefore x is equal to 1. Question 27 on the final exam comes from section P.7. It has not been tested yet. This question is going to see if you can solve absolute value inequalities, and of course, like all other inequalities, can you express the solution in interval notation. Alright, the first one, absolute value x plus 4 is less than or equal to 3. Whenever you're doing an absolute value inequality and you want to do it algebraically, you need to know that the less than symbol interprets as an and compound inequality. So I'm going to write this as x plus 4 less than or equal to 3 and x plus 4 is greater than or equal to negative 3. With one step here, subtracting the 4 out of the middle and off both ends, we get negative 7 is less than or equal to x less than or equal to negative 1. And interval notation, that's negative 7 comma negative 1. Now, another way that you could approach this problem, and I suppose you could do it if you feel pretty proficient in graphing, and it's actually a way that I might prefer to do it because I like to see the problem. If I were to graph this, and I'm going to show you the graph by hand, but we could also be graphing this on a calculator. If we knew the shape of absolute value and we know the transformations, and lucky us, we do, we could sketch a graph of this particular function. Absolute value of x plus 4, so I'm just going to graph this side. Absolute value of x plus 4 shifts 4 units to the left, has a slope of 1, which means it's going to cross 4 units up, there, and same slope heading out to the left, like that. So we get this absolute value shaped graph where the slope is 1 over 1 and 1 over 1 going that direction as well. Now on the other side of the equation, we have 3. 3 is a horizontal line at 3 on the y-axis. Now what we want to know is where is the absolute value graph less than 3? Where is the V-shape below 3? And the V-shape is below 3, all this area between this number and this number. So if I could just figure out what these numbers are, and if we've drawn a good graph, we could certainly just count those numbers. This is negative 1, 2, 3, 4, 5, 6. This is negative 7. We could just as easily say that this V-shape is below 3 between negative 7 and negative 1. So I leave it up to you to determine which you feel is the better approach. If you're the visual learner and like to see the problem, then maybe this is the way to go. If you are more symbolic and like the algebra, then this is the way to go. But either way, they both would work out to the same answer. Alright, this next example, I'm just going to give you the algebraic approach, as this is the way probably more of you will do it, as this is the way it was originally taught in class. But again, you could do it either way. It doesn't matter to me. It is a less than. So again, the less than is the and statement. So that's the single compound inequality. So 4 minus x is less than 6 and greater than negative 6. I'm going to subtract 4 off the middle. Give me negative 10 is less than negative x, which is less than 2. And I have to divide by negative 1. Give me positive 10, that flips the inequality greater than x, flips the inequality greater than negative 2. I don't like the way that this looks because these inequality symbols and this compound inequality, these inequality symbols should be going the other direction. So I'm going to just flip the whole thing over. So this becomes, instead, let's write it up here, -2. Notice how the inequality points to the -2. So it's still going to point to the -2x. And the inequality points to the x. So less than 10. In interval notation, this is -2, 10 with rounded parentheses on the endpoints. Question 28 on the final exam is from section 2.6, previously tested on exam 3, number 5. This question is going to test if you're able to find horizontal asymptotes of rational functions. It's been previously questioned about vertical asymptotes. This one's going to ask about the horizontal asymptotes. All right, when you're looking for horizontal asymptotes, what you're doing, or what you need to do, is compare the degree of the numerator to the denominator. Okay, so the degree, we know what degree is. Degree is the power of x, and in this particular problem, the degrees are the same. Okay, that's important. When we have the same degree on top as we do on bottom, then the horizontal asymptote y is simply equal to the ratio of the coefficients. 3 divided by -2, so -3/2. That's all there is to it. In this example, again, same thing, horizontal asymptotes, so we're looking at the degree of the numerator and denominator. And here you see, different from the first example, they're not the same. What you see is that the power of x on top, okay, so the degree of the numerator in this example is less than the degree of the denominator. It's less than because the degree up here is 0, because there isn't one. So there isn't an x, so degree of 0. So we've got a 0 degree and a second degree. And when the degree is less than on the numerator than the denominator, the horizontal asymptote by rule is always just simply y equals 0 every single time. All right, in this last one we see that the degrees are different. They're different again in a specific way. Here you see the power of x on top is 2, the power of x on bottom is 1. So here you see that the degree of the numerator is greater than the degree of the denominator. And whenever that happens, by rule, the horizontal asymptote is none. Okay? There will not be a horizontal asymptote to a rational function when the power of x in the numerator is greater than the power of x in the denominator. Question number 29 on the final exam comes from section 3.6, and it has not previously been tested. I know what you're probably thinking. You're thinking section 3.6. Okay, 3.6. What about 3.6? It's not been taught yet. So not only hasn't been tested, it hasn't been taught yet. Yet it's still going to be on the final exam. You know, had we had one more day available to us this semester, this is the section that we would have taught and covered. But we just didn't, so it got cut. So what I'm going to do is just kind of review / teach it on these 3 example problems. It is something you've seen before. It's something you've seen in Algebra 2, so it's not completely brand new. What it is solving real-world problems involving compound interest, specifically continuously compounded interest. And I hope that you'll see that this is not really too bad or too difficult to do. First example, says if $3,000 is invested in a trust fund paying 4% interest compounded continuously, that is important. What is the amount in the fund after 20 years? Now, for the purpose of this question on the test, you're only going to see one where it says interest is compounded continuously, so we don't have to worry about other cases. The formula for continuous compounding of interest is A equals P times E raised to the RT power. Okay, in this formula, A is the amount of money, but specifically it's like the final amount. It's what you're going to end with. Okay, the P is the principal. P stands for principal. The principal amount, which is what you begin with. Okay, the R is your interest rate as a decimal, and the T is your length of time. Okay, so these are your four variables. With any one of these problems, you have to be given three of them, and you can find the fourth. Okay, so what three variables do we know? We invested $3,000. That's the P. We have interest rate 4%. That's the R. Over a length of time, 20 years, that's the T. So we're going to plug those values in, and we get A equals 3,000 times E raised to the 0.04 times 20. Once you get this far, just use your calculator. Okay, you're just going to type this into the calculator. So I've got on my calculator 3,000 times E raised to the 0.04 times 20. Get both those numbers up into the exponent, and I get 6,676.62. 2 decimal places seems appropriate here as we are talking dollars and cents. Alright, this next example is the same type of problem. It's a compound interest problem. We are compounding interest continuously. When we see that word, we're just going to think A equals PE raised to the RT. Some students call this the PERT formula, so that they can spell it. If they can say PERT, then they can probably spell it and get the arrangement of the variables set up correctly. But you probably want to put this on your note card just as we don't want to forget this problem because it is a rather easy problem to do. So in this problem we have invested $10,000, that's our principal, and our interest rate is 3.25%. After this much time we want to know how much money do we have. So 0.0325 times 15. Once we're set up, we just go straight to the calculator, type all this in, and I get A to be $16,282.41. All right, next example, same thing. It's compound interest problem, continuously compound interest. So A equals P E raised to the RT. We're finding the amount of money if $500 is invested in an account paying 7.5% interest for 10 years. So we type this in to the calculator, and we get $1,058.50. Question 30 on the final exam comes from section A.2, previously tested on exam 1, questions 1A and 1C. I'm testing here, can you completely factor a polynomial expression, but more specifically one that has only two terms. That's what you're going to see on these three example problems. So two-term polynomial expressions. All right, the first example that I'm going to show you is a difference of squares. Okay, how do I know it's a difference of squares? Well, the difference is subtraction. Squares indicate perfect squares. So I'm looking at two terms that are subtracted that are perfect squares. So we begin with the square root of the 4x to the fourth, which is 2x squared and 2x squared. We want the square root of 9x squared. Actually, hold on a second. I'm going to start over completely. It is a difference of squares, but what did I forget? I forgot the greatest common factor. I forgot to look for a greatest common factor. So we're going to back up. We're going to start this over again. That happens sometimes. So let's do this over again. Notice that there are x's in both terms. I'm going to take out an x squared, leaving me with 4x squared minus 9. Now, keeping that x squared, we're going to factor 4x squared minus 9. 2x times 2x is the square root of 4x squared. 3 is the square root of 9. 1's plus, 1's minus. That's our difference of squares factoring pattern, with this example having that common factor of x squared to deal with as well. Next example, we notice that they are not squares, as obviously indicated by the power of 3 on the variable. This one is a difference of cubes. And it's not going to get by me this time. There is a greatest common factor. Okay? I am more than likely going to give you a problem that has a greatest common factor, so you will have to deal with it just as I did on the last problem. Greatest common factor here is 3. Divide by 3, we're left with x cubed minus 27. With the cube factoring formula, they factor into a binomial and a trinomial. We take the cube roots of the terms respectively to the binomial, x and 3. And then to get the trinomial, we square the x on one end, we square the 3 on the other end, we multiply them together for the middle. Some of you sometimes refer to these as SOAP problems, because now fitting in the signs we go same as the first or same as the problem, opposite sign always plus. So you think of them as the SOAP problem, and it reminds you same, opposite, always plus, binomial, trinomial. As long as we can figure out the terms, we're good to go. Alright, in the last problem, again we look for common factor first. In this particular problem we can divide everything by 2x squared, leaving behind 125x cubed plus 8. Okay, so the cube is indicating cube formula. The 125 and 8 are cubes, perfect cubes. Factors into a binomial and a trinomial. Cube root of 125x cubed is 5x. Cube root of 8 is 2. 5x squares to 25x squared. 2 squares to 4. Multiply together, get 10x. And now we do our SOAP, if you prefer. So the problem was plus, so same, opposite, always plus. And that's it.